I hope I'm audible. Yeah. So, hi, I'm Preetham. I'm a PMRF scholar from Indian Institute of Science and TA for this course. So today, in today's session for like week 5, I'll be mainly we'll be discussing the motion of electron inside the electric magnetic field and electric field, how it will behave, and the some concepts regarding the Landau levels, particle in magnetic field, then different kind of transport, how it happens, like ballistic transport and all that. So then I will just quickly discuss the Arnav bomb effect. So these topics are very important for this week, and I have prepared few sample questions, which is like bit similar to what you were given in the assignments. So I hope today's session will help you to solve those questions. If you carefully listen to this session and follow the uh, all the steps whatever I'll be showing it you today. So I'll just share the screen now. I hope it's so yeah. So first question is if you were asked to like 1 second. So the if a moving electron enters uniform and perpendicular magnetic field. So inside the magnetic field, what will be like the electron travels along. So how the electron will travel? I mean, which trajectory electron should follow? So I mean, if this is the given condition, this one is the given condition. Like it's a uniform and perpendicular magnetic field. Okay, so you simply just there are four options are given. You need to just find out what will be the trajectory. So option C is correct over here, circle, because you simply to solve this question, you simply need to apply the Lorentz force, and you know that how the Lorentz force is related to the velocity of the charged particle and the applied magnetic field. It's just Q times V cross B, right? So the electron in magnetic field feel a force perpendicular to their velocity. That's V cross B. So that's a cross product. So obviously it has to be perpendicular to the V. I mean both V and B. So basically electron will travel in that direction. I mean just perpendicular to the plane of V cross B. I mean, where in the plane where the vector for the velocity and the magnetic field lies. Okay. So since their movement is always perpendicular to the force, so the magnetic force is due no work. I mean, does no work, and the electron's velocity stays constant. So it was just as no work done is happening. So basically, there is no change in the magnitude of the velocity. I mean, the speed. So that's why del E is basically half. change in the half in v square. So v is not changed, so v is conserved. So that's why velocity stays constant, but there is a force. So in the which is F equals to QVB in a constant magnetic field. That's why electron feels this force in a constant magnitude, which will basically change the direction of the motion. So this basically change the direction of the electrons. Okay, so which is perpendicular to its motion. So that's why it's basically form a circular orbit. So trajectory will be circular. Okay, so option C is correct. So now the next question is in a chamber, a uniform magnetic field of 6.5 Gauss is maintained, and electron is shot into the field with a speed of 4.8 10 power 6 meter per second, normal to the field. Okay, so now explain why the path of the electron is a circle and determine the radius of the circular orbit. It's the same kind of question what you just solved in the last questions. So exactly same concepts you need to use over here also. So I will just start with the force. So basically the force acting on an electron is always perpendicular to the direction of motion, as I already discussed this thing, and towards the center of the circular path, and hence the path will be circular. So basically what force is basically responsible for this. So if you just equate, I mean, for any circular motion, you know, always there is some centrifugal force that's balancing with the centripetal force. So basically here the centripetal force, I mean, there's a V cross B. Okay. So that's I mean, that's basically both are balancing each other, the centrifugal and the force, Lorentz force. So simply we need to just equate these two forces. So that is mv square over r equals to qvb. So if we just simply rewrite the equation in terms of radius, we'll get the radius which will be equal to mv by qb. Okay, so all the quantities are given. So here m is the just the mass of the electron and v is the speed of the electron. That is also given and gives the electronic charge, and p is the magnitude of the I mean the value of the magnetic field. So if we just simply plug all the values into the equation, we'll simply get the radius to be 4.2 times 10 power minus 2 meter, which is nothing but 4.2 centimeter. Okay, so that will be the answer. I mean, the radius of the circular orbit will be 4.2 centimeter. Okay. So the next question is, suppose the electrons at rest then are accelerated by applying a potential of 3 volt. Okay. Now these electrons enter the region of space having uniform perpendicular magnetic field, which is B. And now you are asked to calculate the radius of the path of the electron inside the magnetic field. So also similar type of questions. So you just need to use the equation that is R equals to mv by pq, and just simply rewrite the equation in terms of whatever information you are given. So just simply rewrite and you will find this thing. The ultimate radius will be root over 2m capital P over E divided by P. So according to this, option B is correct. Okay. Then next I will discuss a bit about the Landau levels. So it's very important topic actually. So basically it deals with like how the particle motion will be in a magnetic field. So with an external magnetic field, the free Hamiltonian, uh, it will the free Hamiltonian that is the p square over twice m when there is no external any kind of field or no interaction in the system, then simply it will be h naught equals to p square by twice m. Now if we turn on or apply some external magnetic field, let's say, then the equation will change. I mean, there will be some other factors will come because of this external applied field. So this simple equation will become to this. This is a conjugate thing momenta. You can also say, I mean, the modified momenta that is pi square by twice m will become P minus QA square by twice m. A is the where A is the vector potential which is associated with the magnetic field, which is related to the applied magnetic field. That's why this term is appearing, this extra thing. So it's the vector potential that defines the magnetic field. I mean, if you just take the curl of the magnetic vector potential, you will get the magnetic field. Okay. So there are another thing. So you will have some choices of the gauges. So now let's say I'm choosing a gauge which is called the Landau gauge of like if you choosing, I mean, you just need to choose one particular value for the vector potential, that is A equals to B naught x y cap. I mean, the vector potential is along the y direction and its magnitude is B naught time x. I mean, it has some X dependence. So if you just to cross check, so the magnetic field is B naught. So B naught set. So the magnetic field is basically acting on the Z direction and it has a magnitude of B naught. So simply just to verify this thing, you just take the curl of the given A, you will end up with getting B naught Z cap. Okay, that's the check for this. So now we have like if we write the Hamiltonian, what we'll get? I mean, simply we need to replace the value A by B naught x y cap. So let's do this and basically term by term you have to do. So I'll just share the my iPad screen also. So just to solve this thing so that it will become easier for you to understand how. I'll also share the screen. Okay. Yeah, so I'll just open my notepad. So see, this is my Hamiltonian. Okay. This is the Hamiltonian. This was the initial Hamiltonian. Okay. Which is p square over twice m. Now we are taking the magnetic field P naught Z. So the Landau gauge, I'll change the color. I don't like red. So the Landau gauge, which I'm considering is basically your A is B naught X Y cap. So simply if you take the curl of this thing, so you will get B naught Z. You can also check that. So it's verified, right? So this is called one of the Landau gauge. So that's what we are taking. So now our Hamiltonian is basically P minus Q A square 1 over twice M. Okay. So, so the thing is, so this is the vector. Okay. So you can simply write in this way Q minus QA dot P minus QA. Okay. One thing though is this, and then Q square A dot P. Okay. This will come twice actually. Right. When will do. So A dot P equals to P dot A, right? That you know from the dot product, this by definition. Another one is Q square by twice M A square, right? So now let's see what is given here. It's very important to do the calculation for this. So A dot P, what will be the so P has one second. P is your Pxx plus Pyy plus Pz Z. So if we simply take A dot P, what will happen? Only this term will exist, right? So Py, that is P naught X. So we write that. So if you just replace this A dot P by Py B naught X, it will become, the whole expression will become 1 over twice M P square Q square Py B naught X. These two will not be there because they will cancel each other. Got it? And then your A square, which is Q square by twice M B naught square X. So that's how you get the modified Hamiltonian. Okay. I'll come back to here. So then, so this we have obtained. Now, if particle are constant to move in the XY plane, so like the wave function, how it will be, right? So this component is psi of Py. This is based on the gauge, whatever we have chosen, right? So that will become e to the power I Py y by h cut times phi Py of x, where Py is the simply h cut ky. So it's valid since h is uh, translationally invariant in the y direction only. So that's why we simply will write this thing. Now, basically, this is the please. You can also do the calculation by yourself just to verify. So now define LB square equals to h cut by q by b, and omega c will be like mod of q b naught by m, and complete the square basically. So whatever you got from here, you just do the calculation. So this is basically a harmonic oscillator, right? If you rewrite all these things, you will see whatever energy eigen equation eigenvalue from the energy eigenvalue equation, whatever you ultimately get, that is giving you some sort of harmonic oscillator ka energy eigenvalue equation, right? Which is at I mean it's not exactly centered at x equals to 0. Because of this, it's slightly off to the center by off center by this much amount of x ka value, which is ky lv squared, and with the energy levels, that is En equals to h cut omega c times n plus half. So the final wave function becomes so n is the here one of the index. I mean, so that I'll tell. So n comma py will become e to the power I k y y times this. This is Hermite polynomials. Okay, this you can also search in the internet. But so this is giving you some sort of Hermite potential. So where so the Hn is the Hermite polynomials of nth order. The energy levels, whichever equation 6 suggests, are called the Landau levels. Okay. So there are many quantum states for every Landau level. That is for a given n, every Py corresponds to a state with the same energy En. Okay. So this is the thing. So please remember this two formula. These are very important for this topic. Now let's say this is also very important. How to calculate the density of states. Now how we will basically calculate the density of states. Okay, this is one of the other very important concept that you need to understand. So suppose you have a system which is a size of Lx times Ly. This will be your area. This will be your area of the rectangle we are talking about. Then the separate using the separation of variables between the harmonic oscillator. Uh, you can simply do this thing delta x equals to delta times ky lb square, which is 2 pi by ly time lb square. So the number of oscillators we can fit into the system, which will become see from here you can see the x is, I mean this term, right? So from simply from here you will get the value for the delta x. I mean then this will be the separation. I mean this is shifted harmonic oscillator, right? By amount of this. So sim ky value is also you know that will be 2 pi by lb from the 2 pi by ly from the boundary condition. So simply plug it this value in the equation, we will get this. So the number of oscillators that we can fit into the system will simply be Lx by delta x. So it will become Lx times Ly divided by 2 pi times Lb square. Okay. So had we chosen a different case, let's say we now this time we have chosen along the negative x direction. Okay. So minus that would become minus b naught y x. I mean, sorry, this is the given case. So that is minus B naught Y time B naught Y. This is the magnitude and it's in the negative X direction. Then we have at N equals to Ly by delta Y. Yeah, Ly by delta Y, which is nothing but Lx Ly by 2 pi Lb square. So plugging in LV square equals to H cut square H cut divided by QB. We see that for electrons, it will become B times Lx Ly by H cut by E. Simply, we can write this by phi by phi naught. Okay. So N is the number of the flux quanta. So which is a measurable quantity though. Okay. So it is comforting that N is gauge invariance. I mean, whatever gauge we are choosing, you can see it is giving us the same result. So that's why N is gauge invariance. So invariant, and since physical quantities should obey the same physical physics regardless of the description, the choice of gauge is a choice of description of the physics, much like coordinates. But this choice of description should not affect the result of the underlying physics. This is very, very important thing that you need to understand. It's kind of fundamental thing. Okay. So now Yeah, so for so how the current basically flows and what will be the related equation for the electric field current inside a conductor. So this is the traditional view of the conductor. So which is the length is L and the cross section is A, and current is flowing from this point to this point. So we have applied a voltage. So the electric field inside the conductor basically is V by L, and the current density will be from the Ohm's law. We know it will be sigma E, right? Sigma, where sigma is the conductivity, and I will be your the number of charge carrier that is flowing per unit time, uh, per unit area, current density per unit area actually. So I mean it will be A times J, so A times sigma E. So it's becoming V over R, as you can see directly from Ohm's law. Now the what is the conductivity? It's simply 1 over R, right? It's the sigma A by L. So the power dissipation in the conductors is the energy continuity equation tells us the power dissipation per unit volume of resistor. It is J times C. If we replace the value of E by J by sigma, then it will become J square by sigma. So the power dissipation in the entire resistor is, I mean, it's VI, right? So, so you'll get I square R. Now one question regarding this thing. So one sample question so that you get a better understanding. So yeah, it is the electric field of 1 volt per meter is applied to a boron doped silicon semiconductor slab having a doping density of 10 power 16 atoms per centimeter cube, and at 300 Kelvin temperature. Now determine the resistivity of the slab. So some of the information are given. So just consider the intrinsic carrier concentration of silicon at room temperature is 1.5 times 10 power 10 per centimeter cube. So I mean this is per volume actually per centimeter cube, right? And the mobility for the holes is 5,500 centimeters per whole second at 300 Kelvin, and the electron mobility is 1300 centimeters per whole second at 300 Kelvin. So four options are given. You just need to calculate and then uh, you have to choose the right one. So the concept is basically for a semiconductor slab doped with excess charge carriers and placed in an electric field. The current equation is given by the J equals to sigma times C. So where J is the current density and sigma equals to the conductivity of the semiconductor defined as sigma equals to Qn mu n plus Qp mu p. Okay, that has two types of charge carrier are there for, I mean, that is for electron and hole. So N is where N is the excess electrons contributing to the current conduction, and P is the excess hole contributing to the current conduction. Okay. So also the resistivity is defined as the reciprocal of the conductivity. So it will become 1 over Qn mu n plus Qp mu p. Okay. Now the calculation part. So the given silicon semiconductor is doped with boron impurity, right? So for this, so for this case, it is given key Na, the acceptor number density is 10 power 16 per centimeter cube. p type, and q is, 1.16 power minus 19 coulomb, and mu n and mu p information were also given. So the excess electrons from the mass electron theorem, like, it's excess electron is given by naught equals to ni square by capital N. So since Na greater than Ni, right, we can assume that the conduction current exists only because of the acceptor impurities. That is because of Na. So sigma, simply you can write sigma equals to Qna times mu p. And rho is the resistivity of the slab, which is 1 over Q capital Na times mu p. So we'll put all the respective values and we'll get the resistivity to be 1.25. So option 4 is correct. Okay. So now the quantum transfer through the mesoscopic system. So one is the ballistic, first one is the ballistic, second one is the diffusive, and third one is the adiabatic. Okay. So three type of transport here. One is ballistic, another one is diffusive, and another one is adiabatic. So the characteristic velocity for the conduction and the mean frequency I will discuss briefly. So the characteristic velocity is the average velocity of those electrons that uh, contribute to the conductivity, right? So this is how we get this expectation value for the v square. So this is the simple integration you can take. And for metals and heavily doped semiconductor at low temperature, this will become Fermi velocity. Okay. For low doped material at high temperatures, it will become root over dkt by m. So, and the mean free path. Now I'll come to this. So the mean free path L is defined as the average distance an electron travels before scatters. Okay. So it is given by L equals to it will be Vt. So root over this is the RMS. Root means square velocity. Okay. So root over expectation of the V square times the tau, where tau is the scattering time. Now, what is the ballistic electron transfer? So the length scale that is involved in the smallest transistor and nanoscale devices, such as carbon nanotubes and molecular conductors, can be small enough so that electrons do not scatter during the time it takes to travel through the device. So these are the typical examples, and this is for the Intel's 30 nanometer transistor that you can see, and carbon nanotube resistor, and this is the separation is almost of the is 18 nanometer. This single atom transistor. So when the length tail of the conductor becomes much smaller than the mean free path, the transport is termed as ballistic. Okay. So meaning that electron do not scatter during the time it travel during the time it takes to travel through the conductor. So this is the important condition. I mean, this is the required condition for the ballistic transport to occur. This L is very small than the system size is very small, small or lesser than compared to the mean free path of the system. So question: what will happen when L is less than N? The formula for the conductivity that we have, the scattering time tau in them are clearly no longer valid since there is no scattering. Okay, so tau is infinity. So that is the thing. So now the diffusive regime. So diffusive ballistic, these are actually uh, it is it has been shown in the schematics that you can see over here, and at scales longer than L, transport looks basically diffusive, right? So random walk of step size of L. So the diffusion constant, which is how it is related to the Fermi velocity. So it's so constant is 1 over d times Vf square time tau. So dimensionality d is that for the diffusive process. So that is for a simple sample of length L, wide W and thickness T. This you can see how the width and length are there compared to the mean free part. Okay. So this is the diffusive where basically system size is greater than the L. So electron will undergo some scattering that has been shown here. And for ballistic, there is really, I mean, scattering is very less or almost there is no scattering as the system mean free path is basically greater than the system size. So really is the mean free path of the conduction electron. Lambda is the Fermi wavelength of the conduction electron. So now what is the adiabatic transport? So the third kind of quantum transport is called the adiabatic transport, which happens in the 2D system in the presence of a strong perpendicular magnetic field. In this case, a fine shell of electrons around the Fermi energy splits to form levels called Landau levels. So the magnetic length of the electron, which is root over h cut by EB of the order of 10 nanometer actually, is the characteristic wavelength of the electron in the problem. So if the magnetic length is of the order of the sample size, then the inter-Landau level scattering of the electron is suppressed and then they flow without scattering. So this is called adiabatic transport regime. Now we'll discuss briefly about the quantum interference. So this is a prototypical quantum coherent system. Is the two-slit interference experiment. Okay. So the amplitude, these are the two paths. One path is A, another path is B. So amplitude for path is phi A, amplitude for path B is phi B. So what will be the probability? Simply the square root of the total amplitude. Sorry, the magnitude square of the total amplitude. So that is nothing but the mod square of phi A plus phi B. If we just simply simplify this thing, it will become pi square plus phi b square. So this part is plus the real part of phi star. Uh, I mean, these are the complex number, right? So that will the real part of the pi star times phi b. So this basically corresponds to the classical region, and this part is basically corresponds to the. I mean, it is coming because of the quantum interference. Okay. So the electron beam is traveling in isolation in vacuum. So the elastic scattering, which is basically the diffraction of the electrons state. So coherence scenes over large length scale. Okay. Now, so so now basically I'm going to talk about a bit about like the electromagnetic interaction. So then I'll just this briefly discuss the Arnav-Bohm effect and all that. So yeah, so about some electromagnetic interaction mainly I'll discuss. So with our wave function, so with the particle and so it's going to be looking at how the electric field on the magnetic field and actually in particular the scalar potential and the vector potential on which they are based so can cause the changes in the wave function of our particle. And so we'll first start with the Lorentz force law. which already I have discussed multiple times. So for a particle of charge q, which is moving at velocity v through an electric field and a magnetic field p, so then the Lorentz force will be given by this equation, which is nothing but q times E plus v cross b. Okay. If you ever read anything like constant, this is simple from the electrodynamics. Okay. So you know there is a force. So it's based on the charge. So negative or positive, whatever. So that will basically decide the direction of. So and so what does it mean? I mean, in the nutshell, is a charged particle that. So now, so we have here. So when it moves through the electron, when it moves through an electric field, uh, it's uh, it's going to either be shifted towards the positive if the particle is negative, or be shifted towards the positive if the it was positively charged. So it would be shifted towards the negative, and so that's, I think, most people kind of understand that the negative and the positive are attracted to each other. But this is because of this electric field here. And but then with the magnetic field, which is what we have down here. We have this sort of rules. So the left hand rule with a negatively charged particle, in the right hand rule with a positively charged particle. Okay, so this is given here. So this was a really good figure that I found, except that they level this differently than what I always kind of do for myself. So usually for me, I have basically we pointed along the index finger. Uh, if it's pointed on the thumb, then the so this is the middle finger. Okay, and then the V is on the index finger. Then the thumb is the force basically. So if your particle is sort of moving forward with sort of a perpendicular magnetic field, that's what the cross means, and the cross product for V and P basically. This kind of convention. So that's what the cross product means, and then you get a force that's sort of perpendicular to the both of the those. And so what you end up seeing is here we have a positive charge, and so you have it moving, I guess, sort of this way. Sorry, this way basically. It causes it to actually start curling around. So we get this helical path for our charge particle. And then if this was a negative charge particle, it would be a helical path, but with the arrows pointing in the other way around, like a anti-clockwise or clockwise accordingly. So we see when we do this, obviously, we are altering our particles wave function or the time evolution of the wave function. So it's going to change the time dependent Schrodinger equation. And so I have here. I will leave as again the lecture. So this is very quite simple. And in that, so the Lagrangian of the standard momentum and the standard momentum operator substitution, but it essentially deriving this form. Okay. So of the Schrodinger equation from the Lagrangian, but I'm not going to go through that at this point. But this is our time dependent Schrodinger equation. Okay, so we know it's time dependent because it's right here, which is a function of time, the potential, and so the wave function is basically so. So I just have this highlighted and I have highlighted in the green because this is what. So basically we have substitute with this thing. That's why it has been highlighted in green. I'm just showing that using some sort of standard momentum operator substitution, we end up getting this field. The phi is basically the scalar potential or the electric potential in this, which is a vector. So which is why it's in a whole form, and this is the electric field is equal to the gradient of this potential minus the first time derivative of the vector potential. Okay. So in other words, the electric field is the negative gradient of the vector electric potential, while at rest is not changing. And that is the thing. So curl of this vector potential. In other words, the as I mentioned, the electric field is negative gradient of the electric potential at rest. So now here showing what a gradient is, and so we see that well in a gradient it goes towards the highest peak, so where the function becomes the highest here in this center, but since we have a negative once here it becomes maximum goes highest peak, so where the function becomes the highest and in the center, but since we have a negative here it's actually going to where at the center, but since we have a negative here, it's actually going to where it's lowest. And we know that would end up being kind of like our, you know, that a dip like this. So we have this potential, okay, here, so that we would be like our scalar potential, and then when we take the gradient of that, it will make it into a vector field with all the vectors sort of pointing in towards the west part. Okay, so that is what the electric field is. Then the magnetic field, like I said, is the curl of the of this vector potential, and the vector potential is one of these things that you can't measure, okay, by itself. So, but what we'll actually find with the Carnot Bohm effect is that this vector potential does actually uh, alter the the wave function of our particles, and so it is something that actually exists, but and actually because it is gauge invariant, it's not something that you can sort of measure. So then you know sort of absolute value of it. So yeah, so the scalar potential is defined as the basically gradient of this thing of this. So I guess this should be the electric field is defined as the gradient. So this should be the electric field right here, and is defined as uh, So you can see the both are the gauge invariant, since the gradient is only a difference between the points, and the curl only tells how much something is bending actually. So the following diagram has uniform curl no matter where it is measured. So that is very much clear from the picture. So the vector potential is defined. So is the curl, right? Is the magnetic field. So that's sort of how those things are defined. So since they are not something you can sort of directly measure, so both are basically gauge invariant. That is the thing, as I mentioned. So if you have like a temperature gradient, say you have, like 10 degrees here and 9 degrees over here, like this. 1 second. Like here you have 10, here you have 9. There will be a gradient, right? But here there's a temperature gradient of one. So and same you have 100 right here and 99 at this some other point. So here you have a gradient of 1. So it doesn't matter. That's sort of the numbers that you are using. Okay. So are different from each or that's that 100 is much greater than 10 and 99 is much greater than 9. So what you are looking at is just the difference of them. And so the curl is only tells us how much something is. So I put bending here, which is not a very, I mean, I guess rigorous term. But we can see that in the following diagram, in this diagram basically. So these the vectors arrows get larger and larger as we go farther out from the center. That is clear from the picture, right? So, but we also have to move sort of a greater distance. And so if there is like a person right here, uh, and they are following this vector lines, they will go around at the same here in the like the same period as somebody who is right here. I mean, in this region. So the vector lines are smaller, but there is a shorter distance actually. And so the curl is actually a vector, and that vector would be shown sort of right here in the center. So exactly at the center here. So the circle with a little dot, and it is sort of it is supposed to be an arrow pointing out of the screen. And even if you sort of if you took all of those vectors inside here and sort of doubled the length of them, the curl would not change actually, because all that matters is sort of the difference between like this arrows. Okay, right here. That's the little bit further out, and this arrow here, that's a little bit further. So it's looking at sort of the difference between those. The difference is very important. And so once again, the sort of the actual magnitude doesn't matter. It's just the difference. And so that is a kind of intuitive reason why these are our gauge invariant. Okay. So down here, more precisely, if we take, let's say, 1 second. More precisely, if we take our like this should actually be bold. I mean the A prime vector potential. So more precisely, as I was telling you, the this is the thing using a so so A prime will become A plus gradient of this delta, which is a function of R and T, whereas some function of space and time. So this works because curl of A prime, if we take this thing, this curl of the gradient will become 0. So we are having the same thing. The curl of A prime, this you can say it's one of a gauge also. So curl of A prime equals to curl of A. So the same goes for phi actually. If we make it to phi minus del of delta by del t, so such that the electric field, if we calculate minus grad phi minus dA dt, so it will leaves the E unchanged, since the gradient only cares about the difference in the values, not the values themselves. That's what exactly I was talking just a few minutes back for repeatedly. So here, what's the difference matters, not the exact value. Okay. So if we look again at our News-Schrodinger equation, so we need to substitute that P with a minus, as we are in some magnetic field. So we need the momentum will be modified by minus P minus QA. So if we substitute this substitute the equation with a modified momentum, it will become like this. So if you solve this thing, you will get something like this. Okay, so where the first term on the right, which is minus h cut square delta square grad square of psi by twice m, is just the standard kinetic part of the usual Hamiltonian. Okay, so we all know and the three terms with this are the potential term V from the standard Schrodinger equation. Okay, so the potential in this case has to do with the magnetic vector potential and the electric scalar potential. So now the vector potential is the real thing. As I already mentioned, this can be seen with a very long solenoid, which is B equals to mu naught Ni by L. So you can see how the magnetic field lines are there in a solenoid. So current is basically flowing in this direction. It's entering and then leaving. So this is how the magnetic field is generated and following this direction. So a sufficiently long solenoid has a uniform magnetic field inside. So if L is infinite, it will almost become, all the field lines will become parallel and equispaced. So as it is finite, that's why it's basically the curvature is there. Also there is a turning after a certain time. But if it's very long, we can approximate it to be uniform inside the solenoid. Okay, the magnetic field value will be uniform, and also on the outside. So it approaches zero as the length goes towards infinity. So B tends to zero as A tends to infinity. That's true, right? I mean, uh, so the magnetic flux inside the solenoid is phi equals to B times A. So where B is the magnetic field and A part is the area perpendicular to the magnetic field. So the magnetic flux inside the solenoid is this. So let's say we have a solenoid with a radius a and ring outside the solenoid of constant radius, which is greater than a. Okay. Now let's say we have this thing. Then using the Coulomb gauge, the gradi di yeah, the dot product, the divergence of a is basically zero. Our vector potential will be this. So this, I mean, from this, it's very clear key. It has to be circumferential. I mean, it was a tangent. So A will become pi square B by 2 pi r pi naught. So we'll make pi square by B. And since pi square is the area of the circle inside the solenoid, and so A equals to phi by 2 pi r phi cap. So the factor of 1 over 2 pi r tells us that the vector potential drops as a function of the circumference of the ring outside the solenoid. Since the wave function of particle in the ring only depends on the azimuthal angle, which is phi cap, uh, so we can say that r equals to b and theta equals to pi by 2, and the gradient is 1 over uh, 1 over b d d phi by phi cap. So we also so the factor of 1 over 2 pi r tells us the vector potential drops of a function of circumference of the ring outside our solenoid. And these are the things that I've told you. So we also know that since solenoid is uncharged, the scalar potential is zero. So, and our Schrodinger equation is this, to simply plug in all the values, which is a linear differential equation of the form. So subtract E phi of uh, E psi of phi and divide by h cut square and multiply through by b square and make the substitution. You will get something like this. So these are the solution of the form of this. This is the rigorous math that has been done. So now what is very important, you need to take care of this thing. So the energy eigenvalue will be this. Please remind this formula for this thing. So it will become h cut square by 2 mb square times n minus q phi by 2 pi h cut square. Where n is the integer, can take any value from starting from 0 to like plus minus 1, plus minus 2 and so on. So when in is basically positive, that means when the particle moves around the ring in the same direction as the current through the solenoid and the energy is lower, assuming the Q is positive because of this condition. Okay. So the upshot now I'll just one second. So now I'll quickly discuss the Arno-Bohm effect basically. So let's say when a beam of electrons is split, the two paths moving around a solenoid far enough away that the magnetic field is zero. So in other words, the B is basically curl of A will be zero. Okay. So there is a phase shift that occurs, right? Because if you take the curl, you will see it will become zero. So is the beam split and then is the beam recombined. So what this means is that the placing a phase factor on our wave function is phi equals to e to the power ij phi, sorry, psi equals to e to the power ij psi prime, where g is expressed in this way. So who is the path is an arbitrary reference point, so that the integral is taken over a path from this point to this, and r prime is a function of a spherical coordinate, and theta is constant here. So r prime is a function of r, phi, and d phi. So if you just take care of this value and evaluate the integral, you will basically see g will become plus minus q phi by 2h cut. So in other words, if the phase difference is affected by the magnetic flux, even though the particle beams do not pass through the magnetic field. So the phase is offset by this amount q phi by h cut, where it is plus q phi by h cut for the particle traveling around the solenoid is in the same direction as the current, and minus q by phi by h cut when traveling in the direction against the current. So the phase factor will be e to the power just e to the power plus I q phi by h cut and e to the power minus I q phi by h cut. Okay, then the wave functions will be like this. So this is how it goes, and this is the electron source, and the diffraction is happening. This is the double slit pattern, which is bit shifted that you can see because of the phase factor. So this is what I wanted to discuss. I mean, these are the basic things. So if you understood these things here properly, then I think you will be able to solve the questions, which is basically related to based on today's discussion and whatever sir told I mean, discussed in this week. So please go through all these slides and try to clear the concepts. With the help of this, and feel free to ask me any questions and reach out to me if you have any doubts, any query, anything. So yeah, with this I would like to end today's session. So I'll meet you next week then. Till then, bye.